Hello and welcome to second part of our presentation on microwave passive components. Myself Sanjit Kumar Singh, lecturer in Electronics and Telecommunication Department at Praveen Patil College of Diploma Engineering and Technology. So topics that we have learned in the first part, multiple junctions. Now next we are moving on to the second part, that is ferrite components in this presentation. Particularly the isolator, circulator and gyrator will be studied in this presentation. Unit outcomes expected: to describe with relevant sketch the working principle and operation of the given microwave passive components, that is the ferrite components here, and also to see where to connect these components in the microwave test bench setup. Overall course outcome is maintain passive microwave components and devices. So what are ferrite components? Let's see. A ferrite is a non-metallic material, though often iron oxide compound, which is an insulator, but magnetic properties similar to those of the ferrous metals. The resistivity of ferrite materials could be SIS 10⁻14 times than that of the metals. So what are the common components used? The common ferrites are manganese ferrite, zinc ferrite, associated ferromagnetic oxides, that is YIG. Some special ferrites can handle powers as high as 150 kilowatt in continuous wave mode and 3 megawatt in pulsed mode. So maximum frequency of operation could be very much about 220 gigahertz. So when electromagnetic waves travel through a ferrite, they produce an radio frequency magnetic field in the material at right angles to the direction of propagation. So if an axial magnetic field from a permanent magnet is applied, as well as a complex interaction takes place in the ferrite. So that is shown in the adjacent figure. Effect of magnetic fields on spinning electrons when only DC is present and when DC and radio frequency magnetic fields are applied. So with only DC, axial DC magnetic field applied, the spin axis of the spinning electrons align themselves along the lines of magnetic force, we can see in the diagram. So when the radio frequency magnetic field due to propagating electromagnetic waves is also applied, it is 90° perpendicular to the axial DC magnetic field, so that the electrons precess about their original spin axis. This has the effect of rotating the plane of polarization of the waves propagating through the ferrite and is similar to the behavior of light, which Michael Faraday discovered in 1845. So there is a Faraday rotation principle. As per Faraday's rotation principle, states that if a circularly polarized wave, that is TE11 mode, in a cylindrical waveguide is made to pass through a ferrite rod which has been influenced by an axial magnetic field B, the axis of polarization gets tilted in the clockwise direction, and the amount of tilt depends upon the strength of the magnetic field and geometry of the ferrite. So it is given as beta is equal to VBD, where beta is the angle of rotation in radians, and B magnetic flux density in Tesla, D is the length of path of the ferrite material, and V is the Wordet constant of material used. So this Faraday law of rotation is of importance for the three types of ferrite components we are to study, that is the isolator, circulator and generator here. That's why it is of importance. So now see the isolators. What is an isolator, where it is used, and how it is providing the isolation. So what is an isolator? An isolator is a two-port non-reciprocal ferrite transmission device that allows microwave signal in one direction only. So there is unidirectional flow of energy. On the other side, it is absorbed totally. Used to improve frequency stability of microwave generator. So it is placed between microwave generator and load. An isolator is placed. The adjacent figure, top figure, shows that block diagram. So what are the types? Ferrite isolators may be constructed based on two. The first one, the Faraday rotation, that is used for power up to few hundred watts, and the second one is the resonant absorption type, which is used for higher power ratings. So what is this Faraday rotation isolator? It consists of a piece of circular waveguide carrying TE11 mode, that is the dominant mode for the circular waveguide, with transitions to a standard rectangular guide, and that is TE10 mode, dominant mode for the rectangular waveguide. At both ends, the output and transition being twisted through 45 degree, that is with 45 degree the output comes out from the other end. So how it is happening? A thin pencil of ferrite is located inside the circular guide supported by polyfoam, and the waveguide is surrounded by a permanent magnet, C-shape magnet, which generates a magnetic field in the ferrite that is generally about 160 ampere meter. So that is the magnetic strength, 160. A typical practical X-band is in the frequency range 8 to 12.4 gigahertz. Device may have a length of 25 mm and weight of 100 gram without the transition. So in the adjacent figure we can see the Faraday rotation, the different section in that, and the cut wave view is given, and the second B diagram shows the method of operation, how the wave is rotated about in the forward direction and in the reverse direction. So because the DC magnetic field well below that required for the resonance is applied, a wave passing through the ferrite in the forward direction will have its plane of polarization shifted clockwise. So the signal is shifted clockwise to 45 degree through 45 degree in practical waveguide, isolator and circulators by the time it reaches the output end. So from input, with respect to input, the output is 45 degree rotated at port 2. This wave is then passed through the suitably rotated output transition, and it emerges with an insertion loss attenuation in the forward direction between 0.5 and 1 dB. So there is insertion loss when it is connected in say microwave test bench. The insertion loss could be between 0.5 and 1 dB. So in practice it has not been affected by either of the resistive bands because they are at right angles to the plane of its electric field, as shown in the adjacent figure B. So question arises, how an isolator and why it absorbs most of the energy when operated in reverse direction. In forward direction there is very small insertion loss, 0.5 to 1 dB, and that is almost unattenuated, it is passing, and in the reverse direction most of the energy is consumed. So you can think of how it is happening this is due to the internal construction of the ferrite Faraday isolator and the resistive attenuators used, the permanent magnet used. So let's say a wave that tries to propagate through the isolator in the reverse direction from port 2 to port 1 is rotated clockwise because the direction of rotation depends only on the DC magnetic field. Thus, when the wave emerges into the input transition, not only it is absorbed by the resistive band, but also it cannot propagate in the input rectangular waveguide because of its dimensions. So the second resistive attenuator placed near to the port 1 will absorb it completely. So this situation is shown in the figure, and it results in the returned wave being attenuated by 20 to 30 dB. In practice, this reverse attenuation of an isolator is called isolation. So we have seen what is the insertion loss, that is 0.5 to 1 dB, and now the isolation of the isolator Faraday isolator is in the range 20 to 30 dB. So what are the applications now? Applications, this type of isolator is limited to 2 kilowatt is the maximum power handling capacity because of non-linearity in the ferrite, resulting in the phase shift departing from the ideal 45 degree. However, it has a very wide range of applications in the low power field, since most microwave amplifiers and oscillators have output powers considerably below than 2 kilowatt. So moving on to the next ferrite material component, the circulator. The microwave circulator, what is a circulator? Microwave circulator is a passive non-reciprocal 3 or 4 port transmission device that uses Faraday rotation property in the ferrite material. We have seen in the what is Faraday rotation and how the rotation takes place in the ferrite material. So that property is also made use in circulator. So what is the property of circulator? It's a multi-port waveguide junction which allows microwave signal from nth port to be coupled to n plus 1th port. Means port 1 will be coupled to port 2 and port 2 will be coupled to port 3 in the clockwise direction. So the first figure we see of a 4-port circulator, and with the arrow mark in the clockwise direction, that means coupling of one port is in the direction clockwise direction. So that is the schematic diagram below. So a 4-port circulator is based on Faraday rotation as stated earlier. Now the power entering at port 1 is converted to the TE11 mode in the circular waveguide, that is the dominant mode for the circular waveguide, and passes port 3 unaffected because the E field is not significantly cut. It is rotated through 45 degree by the ferrite insert, ferrite rod, pencil shape rod we see in the diagram, continues past port 4 for the same reason that it passed port 3, and finally it will come out from port 2. So it has been shifted or coupled to port 2. So port 1 is coupled to port 2 but not to the port 4 when signal is applied from port 1. So down here we see a circulator can be used as an isolator if we are terminating the third port, the isolated port, with a match termination. Now in the adjacent figure we are seeing diagram miniature Y circulator or 3-port circulator with the magnet on bias magnet on one side of the ferrite, and with a suitable magnetic field strength, a phase shift will be applied to the any signal fed into the circulator. If the 3 strip line and coaxial lines are arranged 120 degree apart as shown in the figure, a clockwise shift as marked with the arrow, a clockwise shift and correct terminations will ensure that each signal is rotated so as to emerge from the next clockwise port. That means port 1, input from port 1 will be coupled to port 2 and output will come from port 2. Typically 12, the typical dimension is 12 mm height and 25 mm in diameter. So it can handle only a small powers. Isolation of the circulator could be 20 dB. Insertion loss is of the order 0.5 dB and standing wave ratio of 1.2. All these parameters are for the X band. So for the different band of microwave frequency, different value could be there. Now the applications are, it is used, circulators are used in radar to isolate transmitters from receivers sharing common antenna. Then it can be used for providing isolation of input and output in the parametric amplifier. It can be used in tunnel diode. So these are the major applications of circulator. Third, the gyrator. The gyrator, what is a gyrator? Gyrator is a 2-port passive linear non-reciprocal ferrite device with a relative phase shift of 180 degree in the forward direction and 0 degree phase shift in the reverse direction. Means when the signal is traveling from port 1 to port 2, as we can see in the diagram, there is 180 degree phase shift, and in the reverse direction there is 0 degree phase shift. So it has many advantages due to this property and many applications. So gyrator is related to a gyroscope by an analogy in its behavior. It consists of a circular to rectangular waveguide inside where transition takes place both at dominant mode, from circular dominant mode to rectangular dominant mode. A twin circular ferrite rod tapered at both ends is located inside the circular waveguide surrounded by permanent magnet. So magnet is important, which generate DC magnetic field for the operation of ferrite. A rectangular waveguide twisted by 90 degree is connected by input and reduces attenuation, provide a smooth attenuation of polarized waves. So that is a gyrator and how it is operated. A symbol we are seeing in the diagram below. Now what are the applications? A gyrator can be used to invert the current and voltage characteristics of electrical component. For example, a capacitive circuit can be made to operate as inductive circuit, or a series LC circuit can be made to operate as parallel LC circuit. Then it reduces the cost of a system by removing the need for a bulky, heavy and expensive inductors, because it can function like an inductor. Then it can be used for IC technology. It is also widely used in hi-fi equipment like equalizers, FM transmitter, pilot signal filters. It is used in data access arrangements, DAA. So What is this DAA? DAA is data access arrangement that provides a customer interface to the PSTN, and in telephony devices also it is used, that connects to a POTS system, that is the plain old telephone service, the standard telephone service that most home uses. Then what we learned in this presentation, here is the summary of mostly we covered in this presentation the ferrite components as the passive component for microwave device, the isolator, circulator and gyrator. What is a ferrite? A ferrite is a non-metallic material, though it is iron oxides compound, which is generally insulator but has magnetic property similar to those of the ferrous metals. Then we saw the isolator is a two-port device. Even a circulator can work as an isolator. So a source to load direct connection may result into back reflections due to any mismatch or due to incorrect impedance matching. That will reduce the efficiency of the source or generation capacity of the source, changes in the or variation in the microwave signal generated. So in order to provide isolation between the source and the load, mismatch load, we are making use of the isolator in between, that will absorb any back reflections but allows signal to pass in the forward direction. So there is a arrow mark on the isolator generally that shows the direction of coupling. Then down we saw the Faraday rotation. What is Faraday rotation and how the signal is shifted by 45 degree from port 1 to port 2 in the forward direction, and how it is absorbed in the reverse direction in the same isolator but from port 2 to port 1. Then we saw the circulator that can be used as an isolator by terminating the third isolated port by a meshed termination. Then we saw the 3-port and 4-port circulator, where a signal at one port is coupled to its clockwise next port, not to the third or fourth port. Then we saw the gyrator, which produces a phase shift of 180 degree in the forward direction and 0 degree in the reverse direction. So that's it. Thank you. The learning resources one can go through for further more detailed deeper learning. Thank you very much.